Wave equation. What is the perfect dielectric medium? How we can define this medium is perfect dielectric, or you have discussion about earlier various Maxwell equation. How we are able to derive the wave equation by the help of some limiting condition by using the Maxwell equation in terms of electric field and in terms of magnetic field. So let's start here, and I welcome you all in this lecture. And we have another lecture earlier also for the electrostatics and magnetostatics. And to being update, you can subscribe our channel so that regularly you will have some update about this. Okay, I welcome you all again, and let's start. So now, in case of perfect dielectric, we know that this conduction current will be equal to 0. So that means J equal to 0. So J equal to 0 is so that J is what? Sigma E equal to 0. So that means sigma is also going to be 0. Sigma is what? Conductivity. And here in case of perfect dielectric, that charge density is also going to be 0. That's why del dot D also going to be equal to the 0 here. And already we have del dot B equal to 0. And now here del dot D equal to 0 since charge density is equal to 0. And we have del cross E equal to minus dou V by dou T and B equal to mu H. So we can write del cross E equal to minus mu dou H by dou T. And again for the another Maxwell equation in the time varying field, we have del cross H equal to J plus dou D by dou T, and here J is 0 in case of perfect dielectric, and D is equal to epsilon E. So finally it can be written as epsilon dou E by dou T. So the similar steps we are going to adapt like a conducting medium. Process will remain same. So here we are going to take the curl of the electric field, that is equation 3, and again there will have some derivative. For that derivative we'll try to find the value, and again we are going to use identity del cross E to find the wave equation in terms of electric field. Similarly, same process will be repeated again for the magnetic field, okay, or that we call wave equation in terms of magnetic field. So finally, these four equations are written as per this perfect dielectric medium. So now here we are going to differentiate the equation 4 with respect to time. So we have here again dou by dou T of del cross H equal to dou by dou T of dou D by dou T. And finally, this D is what? Epsilon E. So this curl operation is the differentiation with respect to a space. So order can be changed here. So equation 5 can be written as here del cross dou H by dou T. So that order we have changed here. Del we have taken first and dou T is taken later. So finally we have del cross dou H by dou T equal to epsilon naught dou square E by dou T square. So this one since D is what? Epsilon E. So this free space is the also called as the perfect dielectric. So in case of free space, okay, we have epsilon as the epsilon naught and mu as the mu naught. So finally, in case of free space, okay, same situation. So now this electric flux density dou D by dou T can be written as epsilon naught dou E by dou T. Whereas magnetic flux density dou V by dou T can be written as mu naught dou H by dou T. So like this, we are able to get the equation 8 here. So next, what process we have to do? Can you recall the previous derivation? Okay. So now we are going to take the curl of the equation 3. And when we'll take the curl of the equation 3, so here we have minus mu naught del cross dou H by dou T. So now we have to find the value of del cross dou H by dou T. And here in the LHS, we are going to apply the identity. Okay. So on the basis of that identity, we have del dot E del minus del square E. This is for the LHS. And here we have similar discussion. So already we have del cross dou H by dou T. So that value we are going to substitute here. Since earlier what we have dou H by dou T, J is already 0. So epsilon naught dou D by dou T. So that value we are going to substitute, and this D we have replaced. Okay, so it is the E. Okay. Since general equation what we have dou H by dou T equal to dou D by dou T. So D is replaced by epsilon naught into E. Okay. So here we have E. So this expression can be written properly here in this way. So that value again we are substituting here. And after applying the identity, we have del dot E into del minus del square E equal to minus mu naught epsilon naught dou square E by dou T square. So similar steps we are going to adapt as we have earlier. Okay. So now finally here what we are seeing that this del square E we got. So how we got this del square E only? How? So this term is going to become here 0. How it is going to become 0? Since we have del dot D equal to 0, since rho is equal to 0, charge density is 0. So finally here del square E equal to mu naught epsilon naught dou square E by dou T is the wave equation in terms of electric field in case of perfect dielectric. So if you see, try to recall in case of conducting medium, so there were the two terms, but here in case of perfect dielectrics in J equal to 0, so we have dou square E equal to mu naught epsilon naught dou square E by dou T square. So this is the second term is same as the wave equation in case of conducting medium, or you can call the general wave equation. In place of mu, we have mu naught. In place of epsilon, we have epsilon naught in the second term, and first term is not available here. Now we'll try to find the wave equation in case of magnetic field intensity. So now what we have done earlier with the electric field, okay, now we'll do for the magnetic field here. So now that what we are going to utilize here, we have del cross E equal to minus dou B by dou T. So finally, if you go to differentiate this one again, so now here we are able to obtain del dot dou E by dou T equal to minus mu naught dou square H by dou T square. Since what we have B equal to mu naught H here in case of free space or perfect dielectric. So now LHS side, again we are taking the curl of equation 4. Okay, so now here what we are saying, if you're trying to find the wave equation in the form of magnetic field, we are finding the derivative of the relation for the electric field, and we are taking the curl of the relation of the magnetic field intensity here. So that's why curl of the equation 4 del cross H equal to del cross dou D by dou T. So finally here we can interchange the, okay, del we can bring inside, and epsilon naught is constant here. So epsilon naught is taken outside, and in place of this value, what do we have? Del cross H. Here also we can apply the identity. So that is going to become here del dot H del, okay, minus del square H. So finally del dot H also going to be 0 since we have del dot B equal to 0. So finally on the basis of that, in this situation also we have wave equation. Okay, so that wave equation is here in terms of field intensity. Which field intensity? Magnetic field intensity. So that minus is negative, negative is going to get cancelled. So we have now finally del square H equal to mu naught epsilon naught dou square H by dou T square. In case of wave equation, in case of electric field, we have del square equal to mu naught epsilon naught dou square E by dou T square. So these are the two different wave equation in terms of electric field and magnetic field in case of perfect dielectric. And this perfect dielectric is also considered the condition of the free space here. So now we are multiplying this means that wave equation now we are writing in terms of corresponding flux density. So here the same wave equation what we have earlier. What is the wave equation? Del square E equal to mu naught epsilon naught dou square E by dou T square. Why I'm writing repeatedly again and again, it can recall and it will go permanently in your subconscious mind. So you're able to remember how we are going to obtain these values. So now in this, if you'll see that what we are doing here, we are trying to rearrange this equation so that how we'll get this equation in terms of flux density. So here we are going to multiply LHS and RHS by epsilon naught. So here we have del square into epsilon naught into E, and finally here we have mu naught epsilon naught. One more epsilon naught is multiplied, so that will come inside. So del dou square epsilon naught E by dou T square. So finally this epsilon naught into E is what? Electric flux density. So del square D equal to mu naught epsilon naught dou square D by dou T square. So this is the expression in case of electric flux density. Similarly, in case of magnetic flux density also we can write. We have field equation, that wave equation in terms of field intensity del square H mu net epsilon naught dou square H by dou T square. So now again here what we have B equal to mu H. So now we have to obtain mu naught into H. So that LHS and RHS, LHS and RHS both sides we are going to multiply it by mu naught. So finally we have del square mu naught H minus minus not negative is not positive is here. So mu naught epsilon naught dou square mu naught H by dou T square. So B is what? Mu into H. So finally here del square B equal to mu naught epsilon naught dou square B by dou T square. So now we have wave equation for the perfect dielectrics, okay, in terms of electric field, magnetic field, as well as in terms of flux density also. So this standard partial differential wave equation frequently can be used in this format, so that we are going to rewrite again here in this standard formats. So finally, if you try to see that here, the general format of the wave, how it is related to the wave equation that we have obtained in terms of electric field and magnetic field. So here general wave del square x equal to 1 by v square. This v is the velocity, dou square x by dou t square. So now if we compare here with our wave equation in case of perfect dielectrics, so what we are able to see here, like suppose for example in case of electric field we are writing del square E equal to mu naught epsilon naught dou square E by dou T square. So if you compare these two equations, so what we are finding here that we have 1 by v square equal to mu naught into epsilon naught. So now finally if you try to rearrange this, we'll get v square equal to 1 by mu naught epsilon naught. And finally, V is what here? Root under 1 by mu naught epsilon naught. So finally, it is 1 by root under mu naught epsilon naught. So this is the same as the velocity of light. So we have to substitute the values. We have already mu naught equal to value 4 pi into 10 to the power minus 7, and epsilon naught value is 10 to the power minus 9 divided by 36 pi. So this is going to give the value for us, which is same as the velocity of the light. So these are the discussion here. Okay. So now finally in another medium, the general equation we can write B equal to 1 by root under mu naught, that mu into epsilon. That in case of Fourier space, what we have? Root under 1 by root under mu naught epsilon naught. But in general medium, in any other medium, this is 1 by root under mu and epsilon. So like this, we got the wave equation for the perfect dielectrics. So what we have considered here, that conductivity is 0. So J equal to 0, since sigma equal to 0, and charge density rho is taken as the 0. Okay. So on the basis of that, we have wave equation in terms of electric field intensity, in terms of magnetic field intensity, as well as there's corresponding flux density also. Okay. So write comments, any doubt is there, I'll answer there. Okay. Thank you very much. Like and subscribe our channel.